All right, in the assignment today, I included a worksheet, PS1, light and energy calculations. I just wanted to go through and make sure that you had some practice on some of these problems. So I'm going to go through and post the answer key to this um, and just work through some of these problems for you and talk about some things you need to pay attention. So real quick, looking at this and going through to this, some of the things you need to pay attention to is what numbers, what things are, and all of that. So labeling this real quickly. Um, Labeling this real quickly, C is the speed of light. Pause this for a second. So C is the speed of light. This little funky symbol right here stands for wavelength. And the V, it's actually not a V, it's another Greek symbol, but that's going to stand for frequency. All right, some things to pay attention to is speed of light is measured, speed of light, C, is going to be 3.00 times 10 to the 8th, and that's in meters per second. So since this is meters per second, we have to pay attention to the fact that wavelength should be measured in meters. Sometimes you'll see it measured in nanometers, but then you have to convert. The video talks about how to convert it. All right, and then frequency is going to be measured in 1/seconds, which can also be written as s to the negative 1 or hertz. All right, so just realize that all of those units are the same thing. The reason why I say use 1/seconds is because that allows you to cancel and get meters, and same thing using meters here, that allows you to get canceled and get seconds and things like that. All right, so it says calculate the wavelength of violet light with a frequency of 750 times 10 to the 12 hertz. So we know C is always going to be 3.0 times 10 to the 8th meters per second. We know that we want to know wavelength, and we know that frequency. We know that the frequency is 750 times 10 to the 12 1/seconds. All right, our formula, C equals wavelength times frequency. So that means that we can manipulate to solve for wavelength. And so that means that wavelength is equal to speed of light over frequency. So plugging that in, wavelength is equal to 3.0 times 10 to the 8th meters per second over 750 times 10 to the 12 1/seconds. A couple of things to note. So when we look at this, just remember for unit cancellation, that gets rid of seconds. And so our answer, we're going to be left with meters. All right. If you want to work this on your own, you can. You need to pause right now and then unpause it, and you can check your answer. Okay, you can go ahead. I'm assuming you've unpaused at this point. The answer would be 4.0 times 10 to the negative 7. All right, setting this one up, it says calculate the frequency. So this time we want to know frequency. Again, C is always 3.0 times 10 to the 8th meters per second. This time we have the wavelength of 530 times 10 to the negative 16 meters. Again, when we set the problem up, our units should cancel. So again, we're only dealing with speed of light, wavelength, and frequency. So we're going to use the formula C equals wavelength times frequency. This time we're solving for frequency. So frequency equals speed of light over wavelength. So that means we have 3.0 times 10 to the 8th meters per second divided by 530 times 10 to the negative 16 meters. So that gets rid of meters. And so our unit is going to be 1 over seconds. Which we can also call hertz, or seconds to the inverse 1, or negative 1. So what I'd like for you to do is go ahead, pause now. After you pause, I will give the answer. Okay, welcome back. So the answer that you should have come up with, we have two sig figs here, so we're going to go 5.7 times 10 to the 21st. Again, just make sure you're checking your math and checking your units as you go through this, and making sure you cancel to get the right thing. If you do it correctly, the unit should cancel properly and you end up with the right units for answer. All right, so the other type of problem that you have with this is calculating energy. So energy, E, is equivalent to Planck's constant and since it's a constant, it's always going to have the same value, which these numbers are in your reference packet. It's also the formulas are in your reference packet. But Planck's constant is 6.626 times 10 to the negative 34. And that's joule seconds. Let me erase that and make that a little more clear. All right. And then remember that V is frequency. And frequency again is going to be measured in hertz, which is the same thing as 1 over seconds, or seconds to the minus 1. All right. Energy is going to be measured in units of joules. So again, calculate the energy. We want to know energy this time associated with a microwave having a frequency of 7.5 times 10 to the 10th hertz. All right, so we know Planck's constant is 6.626 times 10 to the negative 34 joule seconds. We know that we are given frequency 7.5 times 10 to the 10th hertz. And let's go ahead and write this as 1/seconds. All right, so this one we're just going to use the formula as is. So E equals HV. E equals 6.626 times 10 to the negative 34 joule seconds times 7.5 times 10 to the 10th 1/second. All right, so we have seconds in the denominator right there. That cancels seconds. So our answer is going to be measured in joules. All right, so pause right here. Go ahead, do your work, see if you come up with the same answer that I get. All right, if you've restarted the video, here comes the answer. You should get 4.96, or you could do, we only had 2 sig figs, so it'd actually be 5.0. And it's going to be times 10 to the negative 23. Now, this don't seem like a lot of energy, but when you talk about this being over a long period of time, it will become a large amount of energy over time if it continued for a long period of time. All right. On this one, it says calculate the frequency. Calculate the frequency associated with a photon whose energy is 2.65 times 10 to the negative 25 joules. So 2.65 times 10 to the negative 25 joule. We know Planck's constant, 6.626 times 10 to the negative 34 joule seconds. And then we want to know frequency. So in this case, HV, we want to solve for that. So V equals energy over Planck's constant. So 2.65 times 10 to the negative 25 joules divided by 6.626 times 10 to the negative 34 joule seconds. Joules cancels, leaving us with 1/seconds. So frequency is equal to something 1/seconds or hertz. All right, go ahead, pause the video, and press play when you're ready for the response. All right, so this one, you could write it in scientific notation or not, but it's still only going to be 2 sig figs. I'm going to write it in scientific notation, 3 sig figs this time. So it'd be 5 point, not 5, sorry. We get a number of 3.999. So actually this is going to become 4.00 times 10 to the 8th 1/seconds. Now this one is, let me double check my math. Make sure I punched in the right numbers, everything. Yes, 3.99 times 10 to the 8th. 3.999 times 10 to the 8th, which is 4.00 times 10 to the 8th. All right, I am going to go ahead and talk about this. This one was asking for frequency, but what if it would have been asking for wavelength? We don't have wavelength in this formula. You could do 2 separate problems, or you could rewrite this equation. Energy equals Planck's constant, and replace V was, remember that frequency is equal to um, C over wavelength. So we could rewrite this equation as Planck's constant times wavelength. Planck's constant times the speed of light divided by wavelength equals energy. So we could go ahead and plug it in like this, or if we were solving for wavelength, it would be Planck's constant times the speed of light divided by energy. So just realize that you can combine these formulas to get other answers or to get different information depending on what you have. So you're not just locked into one thing. All right, going over back side of this page was just labeling the parts. So this is really fifth, sixth, seventh grade stuff. So just kind of looking at what things is. So looking at number one, it's showing the distance from the top of one wave to the next identical part of the wave. That is going to be called wavelength. All right, which we designate with this symbol. Two is the height from the resting position to the top of a wave. That is going to be called amplitude. And then this point at the very bottom of the wave is called the trough. And this point at the very top of the wave, whoops, got my numbers mixed up. So number 3 would be the crest, which is the top of the wave, and number 4 would be the trough, which is the bottom of the wave. Just wanted to go ahead and go through that just in case you had some issues with it. All right, this is one of the problems from Chem 101. I've noticed that a few people are missing this one, and I wanted to go ahead and make sure that you recognize some things on the setup and recognize some things on why you might be missing this problem. All right, so first thing, it says determine the energy of a photon with a wavelength of 361 nanometers. All right, first thing that should stand out is wavelength needs to be in meters. So first thing you have to do is convert to meters. And then it gives you Planck's constant, and it gives you the speed of light. So in order to solve this problem, we are solving for energy, but we're given, the formula that we are typically given is energy equals Planck's constant times frequency. We don't have frequency, we have wavelength. So if we remember that frequency is equal to speed of light over wavelength, we can actually replace frequency here with speed of light over wavelength. All right. So again, now, again, we need to make a correction for wavelength not being in meters here. So we will have to do that conversion first. Okay, so one of the things to notice, looking at this problem, some of the things to notice, again, this is in nanometers. We need to convert to meters. I apologize that I left it recording while I was looking up something. So one of the things we need to know, don't know what happened there. One of the things we need to know uh, is that 1 nanometer is equal to 1 times 10 to the negative 9 meters. Um, so if we want to convert first, we can go 361 nanometers times 1 nanometer, or sorry, 1 times 10 to the negative 9 meters over nanometers. That gets rid of nanometers and will give us meters. All right, so there are a couple of things that should be familiar to you with these. One of the things that you're always going to look for whenever you're converting to meters from nanometers, um, basically, if you have a number that's in the hundreds place, like this one, 361, what you're ultimately going to end up doing is going to become 3.61, and you should always end up with an exponent at or near negative 10 times 10 to the negative 7. Um, so go ahead and setting this problem up from what you have in the given. Um, we're solving for energy, and that's going to be equal to Planck's constant, 6.626. All right. The actual problem on Chem 101 doesn't ask you to get the units, but I wanted to go ahead and show you unit cancellation anyway. So I pulled my units over to the side just so that you can see it a little easier. I'm going to change colors so you can see which units I'm canceling. All right, so seconds cancels here, and then meters also cancels. So your answer, energy, should always end up being in joules. Now, um, I am not going to solve this and give the answer out for this. I do want you to plug it in. So I would treat these two, I would do these two first, 6.626 times 10 to the negative 34 times 3.0 times 10 to the 8th first, and then divide it all by 3.61 times 10 to the negative 7. And you should get the correct answer there.